Hi, my name is Igor, and I'm software engineer in Airbnb. And today I'd like to talk to you about Sputnik, a framework on top of Apache Spark, which we've built in Airbnb to help with data engineering. Let's talk about typical Spark job which we are running in Airbnb. We're reading data from Hive, we are writing data from Hive, and we are processing 1 day worth of data. If we would try to process historical data every day when we are processing the data, it would be too heavy of a job to run daily. So daily we run a job which takes the data for previous day, process it, and generate result in like result Hive table for partition of that particular date. And if you look at such typical Spark job, how it would look like, you would see that it has a lot of logic which has nothing to do with the business logic of our application. This logic is more about orchestration of running this job. On the slide, you can see that we need to parse our arguments from console to be able to understand what kind of run of the job are we doing. We need to create Spark context so we can run our Spark application. We need to filter out the data for the date with which we are working with. After that, we need to write our business logic and process this data. And then we are writing our data to the result table. As you can see, percentage-wise, the real logic which represent our business logic is just fraction of a job, and it creates problems for maintaining big number of such pipelines in the organization. You are starting to get code duplication between different pipelines because they are all very similar in a way which they are parsing the arguments and do the filtering of date. And another problem is this job relies on the idea that you can process only one date at a time, which can be not very useful if you need to backfill 3 years worth of data, but like run of every job is like 2 minutes, which happens sometimes for not so heavy tables. But to be able to run this job for a bigger period of time, you actually would need to go to this Spark job and change the code of the job to be able to run it for a big period of time. It's just one of the problems. Generally, the problem is when you have that engineer writing a pipeline, it's not ideal that data engineer should implement orchestration, basically infrastructure logic, and not just only business logic. Data engineer, at the end of the day, is very good at understanding the business requirements and translating the business requirements in the code, which can process this data according to the business requirements. So if we talk about and the reason for that problem is that Spark is general purpose execution engine, which is great if you have big diversity of application within the organization. It's great for the execution engine because it can support multiple data sources, multiple languages, and multiple execution models like Spark SQL, like machine learning, like graph processing. It allows you, given very different requirements of your organization, to use a single execution engine to run to be able to satisfy these requirements. And it's like a big feature of Spark. However, this is not particularly great if you have majority of your pipelines following certain pattern. The pattern which we have in Airbnb for 99% of our pipelines is that they are written on Scala. They use either data frame API or something like Spark SQL, and they read the data and write the data from Hive. It means that all the flexibility which Spark is great for is not very useful when you thinking about providing good environment for average data engineer in Airbnb to write their jobs, because this flexibility creates ambiguity, and it doesn't suggest really good data engineering practices, or like easy guidelines about what your data pipelines should consist of. So when we think about what data engineers should actually do on a day-to-day basis, then you would see that data engineers should implement something like simple transformation code. It should get some data frame as input, do all necessary transformation according to business logic to produce an output, and actually it should be all that's really required from data engineer in terms of building the pipeline. And to be able to clearly state which falls under data engineering domain and what falls under infrastructure domain, let's probably break down all the logic within application to big buckets. There is job logic and there is run logic. Job logic is something which data engineers should define. It's business logic, for example, like counting unique visits for every URL. Some pipeline can do that. And job need to specify what is input table, what is output table, what is partitioning schema for this table, and it should provide some information about how you validate the result before writing to output table. But run logic can be handled by some piece of infrastructure, some framework, and we wouldn't want to require data engineering to implement it. It's logic like running a job for a specific day, and this job should retrieve this input only for the date from input table. When we try to write data to some table which does not exist, we should create this table in Hive metastore. And with this separation in mind, we created a Sputnik. Is a framework which tries to take all the responsibility regarding orchestration logic and leave like data engineer with implementing business logic. So how the typical Sputnik job looks like? You are getting your data from Hive, you are running some business logic, and you are writing your result. When you are getting your data, you are reading not directly from Spark API or like Hive API, you're reading from Hive table reader, which is part of the Spark. This table reader take into account console parameters which were passed during this run of the job. For example, parameter for which date we are running this application. And Sputnik reading this data from Hive table get taken into account what kind of run of this job we are making. When you are writing your result, again, you're not writing directly to a Hive, you're writing through table writer, which is part of the Sputnik. And for example, parameter which can be taken into account is what environment are we writing in? Is it developer environment? Is it production environment? So when table writer writes to Hive, it does all this kind of logic which you would require to do if you wouldn't have Sputnik as your framework. So the typical Sputnik job code would look like that. So you have some job, which is object. You extend Sputnik job, which is straight. You read some data from Hive table reader, and you're passing information of which table you're reading from. You're processing your result. It's like business logic, which you should implement. And you write your data with Hive table writer, where you pass your result and you pass your table name. As you can see, you do not do anything regarding creating Spark context or filtering out DS or specifying how exactly to write your data to Hive. All this logic handled by Sputnik. You run your job the same way you would run any other Spark application. Sputnik has Sputnik job runner, and you pass as a parameters the class of your job, as well as parameters for that particular run. Uh, when you're writing your data, in Sputnik, there are two ways to write your data. There is a data frame approach we already seen on previous slides, where you are passing your data frame and you're passing inf information about which table you're writing. Uh, and there is a dataset API. There is another problem in data engineering, which is not addressed by any existing piece of infrastructure, which has to do with schema management. Uh, our data engineers used to do next thing to be able to run their pipeline for the first time. They needed to go to Hive, created a table to which they are writing, and add the meta information about this table, like description of the table, comments, how the table is partitioned, and then they run their job and write the data to that table. The problem with that approach is that they have some DDL script, which often is not even checked into Git. Even if it's checked into Git, it's not getting updated when they run some DDL to change their table definition. So effectively, we don't have a single source of truth for schema definition. You have your data frame as part of your Sputnik application, and you have like real table in Hive. Um, Annotations on case classes in Sputnik tries to address this issue. You can annotate your case class, which would be the source of truth for schema management, and Sputnik would rely on these annotations to create table in Hive with create table statements and all this DDL. Annotations consist of like obviously table name, to which table you are writing, table description, information about what this table is about, table format, Parquet, RC, how you want to store your data, comments on particular fields, another information to which allows you to add more comments to your table. Partitioning schema. You want to specify information about how you're partitioning your data as part of like specification of the schema of that data. And another funny functionality is fields formatting. You see, in Hive, the convention is to follow snake case formatting. When in Scala and in Java, it's camel case. It's not a big deal, but a lot of our internal users and Airbnb really asked to convert the names of the fields from one convention to another convention while you're reading or writing the data. It's not a big deal. It sometimes create additional problems when you try to debug your job and understand like what's going on. But generally, like it allows you to follow conventions of the language you're working with. Let's talk about what Hive table writer does so we can understand why we actually need to have this intermediate layer between us and Spark plus Hive. First of all, it's create table statement based on our either data frame or our case class we are passing as part of dataset API. And we are doing it if this table does not exist. It updates table meta information with description and comments like we described before. It normalizes data frame schema according to output Hive table. There is actually a bug which we ran a lot when we had some applications writing directly to Hive. The problem is that if you change the order of your fields in your result data frame and they are the same type, you're not getting any exception that something is going wrong. But at the same time, you're writing the data for one column into other column. Sputnik has all this logic which looks at the result Hive table and try to adjust data frame according to this result Hive table. There is a problem which used to be very important when we had HDFS and becomes less important with S3, but still like has cost implications, is repartitioning before you're writing your data so you can reduce the number of small files. If you're not doing anything and you have some join like operations, um, some wide operations, you are getting the same number of files as number of reducers as your final stage, which for a lot of our jobs is a big number, like 2000, even when the number of data, amount of data is not very big. It resulted in us having like multiple files, one megabyte or even kilobytes in size. So we are actually repartitioning our result before writing to Hive, so we can reduce this number of result files on disks. We run checks on the result before writing it, and I will talk a little bit more about in next slides. And we support notion of the environment. So we have staging environment, production environment, testing environment, and we change the name of the table based on that. And it's a responsibility of Hive table writer as well. When you read your data, you again can read either in data frame friendly API, where you're getting just your data for name and you need to pass information about your table name, or you're reading in dataset where you're passing the name of your case class and some information about some adjustment to filtering out DS from your input table. As I mentioned before, Sputnik implicitly filters out the data based on date from input table. But sometimes you need to adjust like the logic around this filtering. For example, you every day process data for the last 7 days to find some averages for the last 7 days. Sputnik allows you to do these modifications through date bounds offset. And the logic which we are talking about in scope of Hive table writer, which is running your job in environment-specific way, like adjusting the names of the tables. It works for Hive table reader as well. If you're running your job and you specify like read environment to be testing or production, it could adjust it as well. Spark is really great for unit testing your application. It provides Spark local context, which allow you to run your Spark job in the same Java machine, in just a single Java machine, which is very useful when you are running your unit test during like Gradle build or Maven build stage, and within the same Java machine without spinning out any Docker containers or go into any cluster, you can run your job. It's a feature which has a very big advantage comparing to Hive, where you need to go some troubles to really run your SQL script. And it was one of the big reasons why in Airbnb we decided to move majority of our pipelines from Hive to Spark. Another big advantage for unit testing in Spark is that you are writing your pipelines in Scala. It means that you can break down your pipeline into smaller pieces of logic and unit test these different pieces of logic separately. But there is some limitation to what Spark has to offer in terms of unit testing. There is this nice project, Spark Testing Base by Holden Karau, which was a big influence into testing functionality within Sputnik. And what it provides is some singleton Spark session. So multiple tests wouldn't create their own Spark session, so we wouldn't have too much overhead on launching Spark while running multiple tests. Sputnik provides data frame comparison. It provides loading data from CSV or JSON. We found that for us, it's easy to store this input and output data in the resources files rather than to just add it to like Scala code. And we are doing a cleaning of Hive between our runs. So your typical test for your Sputnik job would look like that. You are reading your input data, from some CSV JSON, and you write this data to Hive table. Then you run your job, and then you compare the result of your job, which is in Hive again, with some expected result. You can pass, when you run your job, you can pass for which specific date you're running your job. You can pass all the parameters which you would have passed if you would really run your job in production. So it tries to emulate running your job as closely as possible to a real life scenario, being reading from Hive, writing from Hive, and taking into account all parameters which you can pass to your job. Another functionality of Sputnik is working with configurations. It serves two purposes. First, it's a good place to extract all your Spark configurations. So you can have job-specific Spark configurations and you wouldn't have to put it like in your Scala file. You can, if you use data frame API, specify all the meta information about your Hive table. And you can pass some configs which are your job specific. In the example on the slide, you can see that in config on the right, we specified some value for a certain key. And within Sputnik job on the left, you can get access to this key. When we write in the data to our output, a failed job is not the worst thing which can happen. The worst thing which can happen is us writing the wrong data, because it would trigger downstream job to start processing our data. So when we find the issue and fix our issue, it's not just we need to rerun our job. We need to communicate to all downstream consumers of our job that happened, and then they need either rerun their jobs or even might do something more to fix the issue. It means that it's very important to check result before writing to a result table. So in Sputnik, there is this trait check, which you implement to define a check you want to perform on your result data. And Sputnik comes with a set of predefined typical checks for possible scenarios. Examples would be not empty check, that you are checking that the result of the job of run of your job is not empty. And it does that through just reading from this data frame, which is actually your result of your job, and just executing is empty on that result. And you return an option with either error message, something went wrong, or you return none, is everything fine, and the check has passed. And to be able to run these checks on your in your job, you need to pass these checks to Hive table writer, so Hive table writer can run these checks in parallel after running your job. Another big problem when you running your job for a historical period of time is that daily run of your job can be small, like again 5-10 minutes, but you need to backfill years worth of data. So to be able to address that, you pass to Sputnik instead of parameter ds, you're passing start date and end. And Sputnik, when it would read data from input table, it would take data actually for this whole period of time from start date to end date. It means that if you are relying on this functionality, it means that you cannot assume that the data which is coming into your job is just 1 day worth of data. It can be challenging for certain types of applications where, for example, you identify users which you've seen for the first time. You are relying on previous runs of applications, and like it's easy to assume that you're running just for that date. For this certain kind of scenarios, you either need to specify within Sputnik that this job can be run only one date of the time, or you need to change your logic to take into account the fact that you can, like, your job can be run for a longer period of time. And when you're processing 3 years worth of data, it can be like very big amount of data which you cannot process in a single run. You would like to break it down into chunks which you can process one at a time. Like in perfect scenario, something like 2 hours job. So when you run your backfill job, you actually have step size parameter, which specifies how many days at a time you are processing. Here we're saying step size 3, which means that you're processing 3 days of time, even that you are like backfilling for a longer period of time. And we already talked about environments. So Sputnik helps you manage environments. If you have your production environment, then the table from which you're reading and table to which you're writing, it's exactly the same table, which is you're specifying when you write Hive, when you write data frame, or the same table name which you specifies in your annotation. But if you are running your job in a developer environment, then Sputnik automatically adds dev suffix to result table name, which allows you to like run your job on the production and not overwrite production data. And you can override the Sputnik logic about what kind of transformation you are making on the result table name to get to the testing environment. So you can override this logic and change namespace name, or I could do other kind of changes. And right now, Sputnik 3 environments are defined: production, dev, and stage. And you can see what are the standard suffixes we're adding to this table's names. Just to quickly iterate over other parameters which Sputnik understands. You can specify drop result table to be true. It's when you run your job on the cluster and you change some schema or change something about your job, and you don't want previous run of the application to affect this run. So when we have drop result tables, it means that we drop the table before we write to it. We can sample the data. It's not very, the sample logic is not very advanced. It's just like taking 10% of all input data. Again, we can, regarding repartition, we can either say that we want to repartition or we don't want to repartition. If your job takes some arguments, you can pass these arguments through job arguments parameter. And if you have several different scenarios in which you run your job, and the scenarios can differ in terms of what a Spark configuration is, with which Spark configuration we are running, or like what kind of parameters inside of this job. You can pass a config path to some config on the machine on which you're running Sputnik application, and that config would be used as a config from which takes Spark configuration as well as all other configurations. And this is it. Sputnik was open sourced September of last year. It's on GitHub. You can like look it up. And one other thing which I really wanted to underline is that even if you wouldn't use Sputnik as a framework, you still need to think about what kind of work your data engineers in your organization are doing, which can be automated, which can be extracted in some pieces of like infrastructure or some framework which allowed you to have data engineers less work on operations and orchestration code and work more on business logic. And this is it. Thank you.